Hey everybody, welcome back. So we have 4 talks in this session. Xavier is giving the first talk, so let's give him a round of applause.
Thank you. I'm very happy to get an opportunity to speak in this huge room. So today I'm going to present a programming Perl, which means that it's a really trivial result that I like so much that I want to tell you about it. And it's about well-funded recursion. So where am I coming from? I write software in Coq and then prove it correct, and did that for a compiler called CompCert. And one thing I learned is that proving a program written in Coq is not enough to convince everyone. The program part of the Coq development, the data types, the function definitions, must still be independently reviewable by someone who does not understand the proofs and the specs or does not want to. Okay, the program should still make sense. This leads to 4 requirements that I try to apply to my own Coq programming. One is legibility. The function definitions should be easy to read for a competent functional programmer, should make it obvious which algorithm is being used. Then there's provability, so it should be easy to prove properties of the function separately from its definition. I mean, dependent types and so on are very nice and good, but sometimes you don't want to use them, and so it should be possible to prove things a posteriori, after the definition. No axioms. As we'll see, sometimes we are tempted to use axioms, like function extensionality, which I find pretty innocuous, but they raise alarms during review, so you have to explain why you're using them and why they are harmless. And then there, of course, extraction. So the extracted OCaml code should contain, well, no obj.magic, no extraneous computations. It should be clean enough to be debugged, for instance, if needed. Sometimes you've only proved partial correctness, and your program rises or stops on an error, and you have to debug that. And for most programs written in Coq, those 4 requirements hold very naturally. Take, for instance, a recursive function like this Euclidean division and modulus, which is structurally recursive on the first argument A. Well, it reads like OCaml code, so it's legible. Provability is easy. You just do an induction over A and some simplification, and then you're on your own. There's obviously no axioms needed. And extraction will produce idiomatic OCaml code, as much as piano natural numbers are idiomatic natural code, OCaml code. But today, I'd like to speak about well-funded recursive functions. So here, recursive calls are made on arguments that are strictly less than the recursive argument, but not necessarily a structural subterm, where strictly less than is a well-funded ordering. So continuing with Euclid, so this is the greatest common denominator computation, and as you see, the recursion is an A mod B, which is strictly less than B, but not a subterm of B, so it's not structural. And, well, there are plenty of ways to define well-funded recursive functions like this in Coq, like fix, a combinator from the standard library, various Coq extensions, function, program fixed point, equations, or good old proof mode plus tactics. But I find most of them deficient with respect to my criteria. For example, let me say a few bad things about the standard library combinator fix. So this is GCD rec written with fix. So as you see, it's a combinator, so it's a little bit hard to use. You have to swap the 2 arguments because the recursive argument B must come first. And then, well, there's this recursor, which, well, you can make sense out of the type. And then there's some proof obligation inside. So legibility is not great, but that could be tolerated. The one thing that I don't like is reasoning about it. So the first thing you need to do is to prove an unrolling equation, for which the standard library gives you a lemma, fix EQ, which unfortunately doesn't work well with curried functions of 2 or more arguments, because it requires an extensionality hypothesis. So basically it asks you to prove that 2 functions are equal. And I don't know any way of doing that in Coq except assuming functional extensionality. So provability is not that great, and it fails the no axiom criterion. However, extraction produces excellent OCaml code. So the fixed point combinator is gone, and this is what you would have written by hand. So to summarize, with fix, so legibility is so-so, provability is so-so, axioms are often involved, and extraction is excellent. And, well, you can see the other solutions I looked at. So program, for instance, is not good for provability a posteriori. And extraction is not great. Equation is almost perfect except the extracted code. Function is actually perfect on all 4 counts, but it's documented as legacy functionality to be replaced by equation. And what do I mean about the quality of the extracted code? Well, at the top, this is function. It's a perfect. This program fixed point, some extraneous computations in there, extra pairing in particular. And this is equations, so it's getting worse with time. So I'm sorry, Matthew, I know you can do better than that. Okay, and I'm going to offer you yet another way of doing well-founded recursion, which is to go back to the basics. So, as you all know what a well-founded relation is. It's a relation where every element of the type is accessible according to this inductive predicate ACK, which means that all descending chains starting in X are finite. And it's a constructive way of saying that there are no infinite descending chains, and it's an inductive way to say it. And it's so inductive that actually to do proofs by well-founded induction, you do proof by structural induction over a proof of accessibility. And that gives you exactly the induction hypothesis you wanted. And the trivial remark I want to do today is this also works for recursive function definitions. So let's see what it does. So going back to GCD, you start with a definition that doesn't work because it's not structural, okay? And then you add an extra argument, ACK, which is a proof of accessibility for the argument that decreases, okay? And you make the function structural over this proof of accessibility. So, of course, you get a little bit of a proof obligation here, which we will fill later. And now you just have to call it with an initial accessibility proof, which you can get from the proof of well-foundedness of your order. No problem. And so what should we put in here, the yellow underscore here? So not any proof, well, it's a proof of that A mod B is accessible. And not any proof will do, especially not LTVF A mod B, because it must be a subterm of ACK, the original accessibility proof, and it must be transparent. The fact must be obvious to the proof checker. And so I found that an easy way to satisfy those constraints is to use the ACK-inv lemma from the Coq standard library. It's just the inversion principle for ACK. So given the fact that X is accessible and Y is strictly less than X, it gives you that Y is accessible. It's transparently defined, and is guaranteed to return a subterm of ACK. And here, you just need a proof that A mod B is strictly less than B, but this can be any proof, opaque, done with tactics, whatever. And so, well, you can use program, for instance, to fill this hole, or refine, or just an explicit proof term, like this GCD obligation here. And in the end, you get something that is also very easy to work with when you want to prove properties. Basically, well, it's kind of tempting to do an induction over this ACK accessibility predicate, but then you run into dependent induction issues. So just do another well-founded induction over the accessibility of B, okay, and then destruct this accessibility argument. There's only one constructor, okay, so it doesn't create a combinatorial explosion. And then you can simplify the function, and you get pretty much what the unrolling equation in the fixed-based solution would give you. Okay? And now you can reason by case, whatever, and you have an induction hypothesis. So reasoning is very easy, and extraction produces optimal code just because it erases the parts in prop. So in the paper, there are a couple of extra examples. And there's one that I would like to show you, just to finish. So in the paper there's the example of Tarski iteration to find a fixed point of a monotonically increasing operator, and that's again an induction where accessibility of the current point in the iteration. So Tarski iteration is in red here. Okay, you start with bottom, and then you apply F repeatedly until you hit a fixed point, and it's the ascending chain condition, the fact that your order is well-founded, that guarantees that it exists. However, well, people who do static analysis and abstract interpretation use that a lot, but sometimes their domain actually is not well-founded, or sometimes it takes too long to find fixed point. Think of integer intervals, for instance. It can get bigger and bigger and bigger forever. So Patrick Couzeau and Radia Couzeau introduced widened iterations, which is the idea that, at every iteration you will jump a little up with a widening operator nabla. So the next point in the iteration is f of xn widened with xn, and the widening is a heuristic to accelerate the convergence. And so you may skip past the fixed point, but that's already pretty good. And the point I wanted to make is that so this relies on a non-standard ascending chain condition, which is here. So for every increasing sequence x, the sequence defined by applying widening at every step reaches a limit. There's a k at which point it's, sorry, this should be y, at which points yk is yk plus 1, is yk plus 2, etc. And that's a post-fixed point you are looking for. And that can be reformulated constructively as an accessibility predicate of sorts. However, this one has two arguments, x and y, and it says that widened, that for every increasing sequence starting in x and every widened sequence starting in y, you will eventually you will be stationary eventually. Okay, so it's almost like hack, but a bit more complicated. And now you need to prove that for every x, w hack xx holds. And if you do that, then you can use that in a recursive function that will do the widening widened fixed point iteration, again, just by structural induction of a proof of accessibility. All right, so that's all there is to it, really. So wrapping up, that's a simple approach to programming well-founded recursive functions in Coq. Satisfies all my requirements: legibility, provability, no axioms, extraction. No extension to the Coq language is required. The calculus of inductive constructions is all you need. I think it's also more formative for students than just to tell them, oh, just use function or some other black box. It's an opportunity to tell them about accessibility and blah, blah, blah. As I showed, it extends to variants of well-founded recursion, such as iteration with widening. And of course, it's an instance of a much more general pattern, which probably underlies the function mechanism, which is recursion on an inductive description of the definition domain of a function. Thank you. I'd be happy to take questions. Plenty of time for questions. Yes?
Can you wait?
Yeah, you need. The room is so big that you need a mic.
Thanks for the fantastic talk. I use this technique quite a lot, and it's very annoying that I have to redo it from scratch every time. So for every inductive type I have to redefine the right eliminators and everything, and it's very annoying. Is there a way to automate this method?
Oh, okay. You mean automating the so from a data type, automating the accessibility-like predicate that goes with it? Oh, it's an interesting question, actually. Nothing comes to my mind. Okay, I'm not saying it's impossible, but nothing comes to my mind. Maybe some other people want to chime in. Question here. Oh, okay. Sorry.
I once published a paper on that was kind of formalization of widening operators as some kind of well-founded type. And one difficulty there was if you were trying to do some abstract domain, which was a composition of several simpler abstract domains, then you would have to compose the termination arguments, and then the proofs became extremely technical and complicated. Do you have any insight on that?
Not that much. So yeah, I had some experience with some simple domains for data flow analysis, and I know David Pichardy did bits and pieces of that in his PhD thesis too. So the typical example that's difficult, if A is well-funded, then you want finite functions from B to A, finitely supported functions from B to A to be well-funded as well, and that's not trivial. So again, no, I don't have a general technique, but I think basically there's a few constructions that that you have over and over again: lexicographic products, generalized products, sums. So it's a lot of bureaucracy, but it's doable. And I have no idea, however, how this would extend to this widened accessibility predicate. I guess a bunch of the theory of well-funded orders would need to be redone. And maybe it would not work as well. Mathieu at the near the right entrance.
I can do better, but maybe you can do better too, because
Okay.
what you see in the encoding is just currying and uncurrying. When I have multiple argument functions,
I could.
Couldn't OCaml tell me that
it's not my natural programming style, and I think everywhere else in Coq functions are curried. Okay.
Yeah.
So, but yes, in a pinch. And if you curry now, you need an ordering over pairs of natural numbers, which ignores the first component. So you need a non-standard ordering as well.
yeah, you use a measure. But I was actually, it's a real question. I expected that in OCaml, this curried function would be just as performant as the uncurried one. Is there a performance difference?
There may be. I mean, in some simple cases, OCaml is capable of turning a function that takes a pair into a function that takes two arguments. Here, it's a little more complicated because you have this extra function and whatever. So yeah, I would have to look at the generated code to answer.
Okay,
But yeah, I still prefer this one because sometimes I will have to debug it or run it under debugger, you know. So this one is so much nicer.
And then maybe to answer the first question, you can always derive the subterm relation of an inductive and prove that that is well-founded, and that gives you accessibility. To
Okay, so that's a reply to Arthur's
equations
question.
as a derived subterm.
Okay, and that can be done automatically.
Yeah.
Okay, good.
It's actually the justification of structural recursion that that you can use to say that you could reduce any guarded fixed point to one that is just structural on accessibility.
All right.
Order.
Okay. One question here. Yeah. Question there. Question here. Let's do a random walk through the room.
Thank you. So this reminds me of Large G, Wendling, and Monin's Braga method. So did you...
Yeah, well, we started exchanging email after I submitted the last version, the latest version of the paper. So yeah, definitely have to look at what they've been doing with their Braga method and the like. There are certainly connections. I have the impression this, accessibility proofs and so on is a very nice special case. And but yeah, another of my extended examples is with graphs and DAGs, and I think they have plenty of good techniques to deal with DAGs, some of which I don't know. So I really have to look more into what they've been doing.
and I think there is, I worked also on trying to automate it, like connecting it with the general recursion monad from Conor McBride.
Yes.
So I think it's also another possible answer for the first question. But
Okay, good.
take one last.
Yes, well, no, it's your, it's theirs.
So there's one assumption you're making here, which is that if you write in the OCaml subset of Coq, then the OCaml code that you will get will be in the OCaml subset of OCaml. That is no obfs.magic and the like. Is that a desiderata you have for the future of Coq? Because my understanding is that in the way to generating verified OCaml code, the plan is not necessarily to maintain that invariant. That readability of OCaml code is not necessarily considered a priority.
Well,
is that one for you?
Yeah, we see what happens. The extraction facility based on the MetaCoq project, for instance, targets an untyped intermediate language of OCaml and not source OCaml. So maybe I'll have to reevaluate my priorities. I still think it's nice to have a readable and typable camel code. It gives a little more confidence in what we are running in the end.
And debugging.
And debugging, yeah. But well, it's a best effort, okay.
All right, let's give Xavier a hand.
Thank you.